Okay, so we start with the topic. We start with the topic haloalkanes, and so it is known as halogenoalkane also, and they are also known as haloalkanes. It is the same thing. The word halo over here, the word halo over here represents the halogens. Now the halogens, they are general representation is Rx. Generally they are represented as Rx. So when you find anywhere written as Rx, it means we are going to talk about haloalkanes. So for the haloalkanes, the first we will understand what are haloalkanes, how to name them, how to draw the structural displayed and a skeletal formula. Then we will try to talk about the types of haloalkanes. Then we will go through the some properties of haloalkanes, and then we will move on to the reaction. So that would be the way we will be studying it. So over here, when you say Rx, it means haloalkanes, where the group R stands for the any alkyl group. Any alkyl means the carbon atoms and so on. And X stands for that alkyl could mean methyl, ethyl, propyl, any groups. And these are your X stands for the halogens. So halogens means you could have Cl, Br, I, any of this. Now their general name is, you may also find somewhere at many places where they are called as alkyl halides. So that is a general way of naming, but we will follow. So general name is actually the common name. It used to be named before this way, but now we need to follow the IUPAC naming. IUPAC name, or in your exams, they call it as systematic naming. They call it as systematic naming. So in systematic naming, you call the haloalkanes as haloalkanes, where the word for Cl, you will write it as chloro. For Br, you will write it as bromo. For I, you will write it as iodo. And some people ask for fluorine, even though we usually don't use it, we call it as fluoro. So for example, if you have a CH3Cl, so there is a Cl over here, you will call it as chloro, and there is one carbon atom. So for one carbon atom, alkane is methane. So this becomes a chloromethane. Same way, if you had a CH3C, CH3H, and then let us say you have a bromine over here, you will call it as a bromo, and then there are three carbon atoms in the parent chain. There are three carbon atoms in the parent chain, so you will call it as a propane, bromopropane, but then you need to write down the position of this. So position is either side you write, it will be 2. An important thing from this name you can understand is that halogens are considered as substituents. That's an important thing. Halogen is not a functional group. Halogens are not functional group. Halogens are substituents, similar to like methyl and ethyls and so on. So they are substituents. Now, how do I know that? I know it from their name, because substituents you usually write before the parent chain, like methyl something. Like for example, if I was writing the word propanol, so all stands for the functional group, which represents functional group, which represents the OH group, which represents the OH group. But if I was writing 2-methyl propanol, so the name ends in the functional group, and the name before the parent chain name, that means 3 carbon atom, these are called as substituents. So anything written before the parent chain is a substituent. Anything written after the parent chain, that is known as a functional group. Like for example, I can say propanoic acid. Like for example, I can say propanoic acid. Now oic acid stands for the functional group. This will be your functional group, which is your COH group. So the name always ends in the functional group. So from the name itself, it is very clear when I'm saying halo, So we are considering this as a substituent. So halogens are not functional group, they are considered as substituents. Like for example, if I have this molecule, let us say CH3, CH, and Cl, and over here. Now remember, both of them are considered as a substituent. So whether you have the CH3 and Cl, both of them are substituents. That's the first thing. The second thing is, so you will have to select the longest chain of carbon atoms. I have selected the longest chain of carbon atom. I have to number it too. There are two ways of numbering this. One is from left to right, and the other is from right to left. So I write it 1, 2, 3, 4. The other way is 1, 2, 3, 4, this way. Now, when there are two different ways of, or more than one ways of numbering, then you follow the lowest sum rule. The lowest sum rule is you add the positions of the substituents. So the purple one, it is 2 plus 3, that is 5. And the green ones, 2 plus 3, that also is 5. So both of them, the total is the same, that the lowest sum. This is called as the lowest sum rule. So both are the same. You can consider any one of them. So we will let us consider this way of naming, the purple way of numbering. Now comes the name of the substance, this compound. Now here there are two substituents. One is methyl. The other is chloro. Now the problem is which one to write or how to write. The methyl should be written first, or the chloro should be written first. So here you will follow the alphabetical order. Here you will follow the alphabetical order. So depending on what you have, like Cl, Br, I, you will look at the first alphabet here. So if I compare over here, this is C and this is M. So C comes before. So I will have to write 3 chloro, 2 methyl. So you can see the numbering, we are following this. And the naming, we are writing it this way: 3 chloro, 2 methyl, and then there are 4 carbon atoms. So you will write it as butane. The other way possible is you could have also written it as 2 chloro if you were considering the green way of numbering. So you would have said 2 chloro, 3 methyl, butane. Now if you compare this, this is more appropriate, correct, compared to this. Why? Because either way, the lowest sum is the same. So you can prefer any way of numbering, but when you are writing it this way, when you are writing the name this way, the substituent which comes alphabetically first is also getting a lower number. Here, the substituent which is coming first, it is getting a larger number. So it is preferred to use this naming, not this name. If there was a difference in the lowest sum rule, then whichever is the preferred, you will have to write accordingly. Like for example, you could also have, let us say, CH3, CCl over here, and you have a Br over here. And then you have a CH3 like this. Now, in this case also, this is your parent chain. You can number it either way, but both way will be correct. 1, 2, 3, 4, or you say 1, 2, 3, 4. In both the cases, 2 plus 3. 2 plus 3 is equal to 5 for both the ways. But this is bromo. Alphabetically, it comes first. So it is better to give this a lower number. So in this case, you will write it as 2 bromo, 3 chloro, and butane. You will not come across these type of examples, but just to give you the naming idea. You may come across like this type of examples. You have CH3, Cl, and you have Cl and CH3 like this. So in this case, What happens is you have 2Cl, you can write the name any way you want. So numbering from any side, let us say 1, 2, 3, 4. So you would say 2,3-dichlorobutane. So for two substituents, similar substituents, you will use, for similar substituents, you will use the word ditri. For different substance, you will use alphabetical order. As simple as that. If similar substituents, then you use di, tri, and so on. And if different substituents, if substituents are different, then you will use alphabetical order for numbering. For numbering also and naming also, both of them will follow this. So if someone asks me what is a general formula based on I have taken so many different examples, you can add all the carbon atoms and so on, you will find the general formula would be CnH2n plus 1. So from alkane, one of the H is removed. In that place, you are getting the X. Like for example, you had a methane. Its general formula is CnH2n plus 2. You are removing one of the H, and in that place you are adding X. So this becomes CH3X. That becomes the haloalkane. So its general formula is CnH2n plus 1, because instead of 2, you have removed one of the hydrogen and are putting X. So that's why the general formula for the haloalkanes is this. So right now you have learned how to write down the names. Skeletal formula, structural formula should not be different, should not be a difficult thing. Like for example, this, if I want to write a skeletal formula, there are 4 carbon atoms. So I can write 1, 2, 3, 4, 4 carbon atoms. At the third position and the second position, you have the Cl. So this is the skeletal formula. For this one, there are 4 carbon atoms, 1, 2, 3, 4. Second position, Br, third position, Cl. Finish. Over here, if I want to write down the skeletal formula, there are 4 carbon atoms in the parent chain. At the second position, from the right, it is Cl. Third position, it is a CH3. So I have to leave this because this indicates a carbon atom. If I have over here this thing, it is 3 carbon atoms, and then you have a Br. You can write it this way, you can write it this way, down Br. That doesn't mean anything. For this, there is no need because there is only 1 carbon atom. No one is going to ask you to write down the skeletal formula for this. Then we move on to the types. So you can call it as, or you can say this is types of haloalkane, that is a classification of haloalkane. You can also call them as isomers. Why isomers? Because they will be having a same molecular formula. So they could be considered as structural isomers. So there are 3 types. There are 3 types of haloalkanes. One is known as primary, the second is secondary, and tertiary haloalkanes. So primary haloalkanes, it is represented as 1 degree, or you can write PRI dot, or you can write the complete name, primary. Secondary is 2 degree, or you can write SEC, or you can write it complete, secondary. And tertiary is TERT dot, or the full name, tertiary. So there are 3 kinds of haloalkanes. We are already aware of what we mean by primary, secondary, and tertiary. Just a quick look that when you are saying a primary haloalkane, when you are talking about primary haloalkane, it means the X stands for the halogen, is attached to a carbon that is directly attached to one carbon or none. So it is one or none. What does that mean? This means, like for example, I have a Cl attached to this carbon. So what are we focusing on? We are focusing on the carbon that carries the Cl. Now, how many hydrogen atoms it is attached? None. So this is an example of a primary haloalkane. But if you have like this, now what are we focusing on? We are focusing on the carbon that carries the halogen. It is directly attached to only one carbon atom. This carbon may be attached to any other thing, we don't care. But the carbon that carries the function, the Br group or the halogen, it is attached only to one carbon. So this also is primary, one carbon. But what about this? If you have another carbon attached to this could be anything. Then what happens? Is this a primary? Yes, this is still a primary. Why? Because the carbon that carries the halogen, it is directly attached to only one. This carbon is then attached to this. This green one is not attached to the red one. This one, the first one, it is not attached to it. So we are looking at this carbon, the first carbon. So it is attached only to one carbon atom. So all these are examples of primary haloalkane. All these are examples of primary haloalkanes. Now moving on to the secondary. Haloalkane. Now secondary haloalkane, the X is attached to a carbon that is directly attached to two carbon atoms. So the primary was either attached to one or more than or none, but secondary is attached to two carbon. Like for example, this is a carbon that carries the Br. This carbon should be attached to two carbon atoms. So there will be two carbon atoms and one hydrogen. They in turn are attached to what? We don't care. What we care is this bond. Is it attached to two carbon? Yes. So this will be your secondary carbon. What are they attached to? That is none of our business. We need to only focus on the carbon that carries the Br. The tertiary haloalkane, over here, the X is attached to a carbon that is directly attached to three carbon atoms. What does that mean? This means like you have a I over here, you have a C over here, another C over here, another C over here. In turn, what are they attached to, bonded to? We don't care. What we care is this bond. So the carbon which is attached to the halogen, it is directly attached to three carbon atoms. So this is an example of a tertiary haloalkane. So naming, we already know. So right now, we know this. Now I will be talking about a little bit more about the properties of haloalkanes because they do ask in the exam. It is considered as an application basically. It will be considered as an application. So if you go to the and some of it we already know from beforehand. We is just applying it over here. So let's talk about some of the physical properties. Now, when you talk about physical properties, we are mainly concerned with the solubility and the boiling points. But what we need to remember is that if you have any whether it is a primary, secondary, or a tertiary haloalkane, what you need to understand is that this bond is always polar. This bond is a polar bond. This bond is a polar bond. That's the first thing. The second thing we need to understand is, like for example, if you have a CF, you have a CCl, you have a CBr, you have a CI. Now the electronegativity decreases down. The electronegativity in halogens or in any of the groups decreases down. So that means this bond would be more polar compared to the CI bond, compared to the CI bond. So what we need to know is that the bond polarity decreases down the group. So the bond polarity will keep on decreasing down the groups. That's the first thing. The second thing is, so now, okay, what type of interactions will be there? Because now we have to talk about, so that is one important thing about all haloalkanes. Now, when you're talking about the boiling points, when you're talking about the physical properties, the first thing we need to look at is the boiling point, boiling or the melting point, depending on whether the substance is solid or liquid. Now, remember, when you're talking about boiling or boiling point, melting points, you have to talk about the intermolecular forces. What type of interactions are there between the molecules? Now, if you take an example of a haloalkane like this, and then there is another haloalkane molecule, because you are talking about the boiling point, so we will be considering the similar. We will be considering the similar molecules having intermolecular forces. So if you observe over here, this is partial positive, negative, positive, negative. So this part and this part, they will have a dipole-dipole interaction, while this whole part and this whole part being a non-polar part, they will have London forces. They will have London forces of attraction between them. So that is what we need to remember, that in haloalkanes, this is a type of intermolecular force that exists between the molecules, because we are talking about the boiling points. Now, let's suppose, let's suppose I give you this CH3Cl, then CH3CH2Cl, and CH3CH2CH2Cl. Now this part is common, the Cl part is common, same, but what is happening? So the dipole-dipole interaction is approximately the same. That means with this molecule and another molecule of the same kind, this molecule and another molecule of the same kind, this molecule, that is chloropropane and another chloropropane. So the Cl is common for both them, all of them. The difference lies over here, this part. The difference lies over here. So what is happening in this is, as the number of carbon atoms are increasing, or you can say the molecular mass is increasing, molecular mass increases, what is happening? The surface area is increasing. And when the surface area increases, this leads to increase in van der Waals forces. This leads to increase in, or better word is, this leads to increase in London forces. And when the London forces are more, definitely more energy will be required. So based on this explanation, if you are looking at the order of boiling point, the third will have the maximum, then 2. I'm not talking about the isomer, I'm talking about 1, 2, 3, this, and then 1. So why that is happening? Because the surface area is increasing. But there is other possibility also. Like for example, I have CH3F, I have CH3Cl, and I have CH3I. Now in this case, the alkyl group is the same, one carbon atom. So the size is not going to be affected by the alkyl group. The size will be governed by the size of the halogen. Now as you go down, we know this, down the group the atomic size increases, down the group the atomic size increases. So what happens is the iodomethane will have the maximum boiling point, and the fluoromethane will have the least boiling point. Why? Because this have the smallest size, while this has the largest size. So we have compared them on the basis of the difference in the size, number of the carbon atoms, and we have also compared them on the basis of the difference in the type of halogen. Both ways we can understand the difference in the boiling points. Now suppose I was given an haloalkane, an alkane, and alcohol, and asked to compare their boiling points. Compare boiling points, assuming that they are, whenever we are comparing different things, then we are comparing that molecular mass is similar. Because we know if the molecular mass is changing, then we can simply say that more molecular mass means surface area large. But here, these are different, they belong to different homologous series. So we want to compare, but assuming that we are taking examples where the molecular masses are same, so we want to understand which of them has a higher boiling point or a lower. In other words, the order of boiling points. So for that, again, you need to look at the type of intermolecular force you have. Now, just now we have discussed that the haloalkanes, they have London forces, plus they have dipole-dipole interaction, plus the dipole-dipole interactions between haloalkane molecules. The alkanes, they have only London forces. They have only London forces, because in the haloalkane you have the halogen atom that makes it polar, while in alcohol you have London forces, you have a dipole-dipole interactions, and you also have the hydrogen bonds. So based on the type of interactions, definitely this will require more energy, and this will need the least energy. This will need the least energy to boil. So if I want to arrange them in order of increasing or decreasing boiling points, the alkanes will have the least boiling points, then the haloalkanes and alcohols will be maximum. So this is order of boiling point when you are comparing different types of organic compounds. And the reason is based on simple, what are the intermolecular forces existing between them. Another important thing is, if I was given, so we are trying to compare different types of substances, different types of haloalkanes with, and haloalkane with different kinds of substances. Now let us say I have a molecule which is CH3, CH2, CH2, CH2Cl. Another one is CH3, CH2, CHCl, and CH3. The third one I have is CH3. So the first thing you will observe is this is a primary, this is secondary, this is tertiary, and these all have same molecular mass. So basically they all are isomers. So what I'm doing is now I'm comparing the isomers. We already know from the chapter for alkanes that if when you're comparing the isomers, then they have the same molecular formula. Same molecular formula means the molecular mass will be the same. Isomers, they have same molecular formula. So if they have the same molecular formula, that would mean that they have same molecular mass. So the molecular mass is not different between them. Then how do we compare? So if you observe over here, it is very simple that this has the least surface area. Least surface area. Least surface area would mean that least London forces. And if there is the London forces between the tertiary haloalkane is least, that would mean least energy required. Least energy required. So the order of boiling points would be tertiary would be maximum, then comes the secondary, and then comes the primary. In another word, in another way, you can also say that greater the branching, we have talked about this in intermolecular forces chapter. Greater the branching, lesser the surface area. And lesser the surface area means this leads to less London forces or lesser London forces. And lesser London forces means less energy required. So this concept is for isomers because they have the same molecular masses. They have the same molecular masses. Then the solubility. Now, when you're talking about solubilities, then we need to understand that you are talking about intermolecular force between the haloalkane and water. So you need to look at the intermolecular force between them. Now, a straightforward statement is that the haloalkanes are insoluble. The haloalkanes are insoluble in water. As simple as that. That is enough for us. But if you want to explain, you would simply say that the new interactions, I will explain it, but I'm writing it first. The new interactions between the Rx and water molecules are weaker, therefore give out less energy. They give out, because remember, when the interactions or the bonding takes place, they give out energy, give out less energy, which is not enough to break the hydrogen bond between water molecules. In one word, not energetically feasible, because anything will be formed when the energy is lowered or there's enough of energy to break the bond. Now, what if I try to explain it? What does that mean is, let us say you have in one test tube only the Rx. So what will happen? There will be many Rx molecules, that is the haloalkanes. They will have some interactions between them. We already know that. Same way, you have in another test tube water molecules. So there will be many water molecules and they will have some interaction between them. And we know that this is a hydrogen bond, which is a strong intermolecular force. Now, when you try to mix them up, you will mix these two together in one test tube. Now, over here, you will have the Rx and you will also have the water. So they will have some interaction between them. Now, what we are saying is that this interaction is a weak force of attraction. This interaction is a weak force of attraction. So if it is a weak force of attraction, it releases less energy. This releases less energy. Now, if it is releasing less energy, then it is not enough to break this bond, because this interaction is a strong. So that is like, for example, if you want to buy something which costs 100 dirhams and you have only 80 dirhams, you cannot buy this because the money you have is less. Same way over here, the energy given out is less than what is required to break the interactions between the water molecules. So that is what we just said, energetically not feasible, or I should have written, yes, energetically not feasible. That means in terms of energy, it is not feasible because the required amount of energy is not there. So this is what I mean. The new interactions between the Rx and H2O, which is this. This is a new one. When you will mix them, are weaker. So if they are weak, they give out less energy. And when they are giving out less energy, it is not enough to break this interaction between the water molecules. So everything stays their own way. The water molecules are not going to break the interaction among themselves. The Rx molecules are not going to break the interactions among themselves. Therefore, the new interactions are not going to be created. And if the new interactions are not going to be created, it means the haloalkane is not solid. So next video, we will start with the chemical properties. We will start with the chemical properties.